does is to improve upon the Einsteinian model and come up with a different model, an improved version of the model, which is called the Debye model, and see how things go from there. So the basic idea of the density of states is extremely important. So in this module of this course, we are looking at phonons and crystal vibrations. Phonons are quantums of, these are quantized particles. These are excitations inside the system which describe lattice or crystal vibrations. And they heavily depend upon how we describe the density of states. The same idea of the density of states is also extremely vital to understand how electron waves inside the crystal propagate, and that will be our third and last module of this course. So it's important that we understand the density of states fully. So in the Einsteinian model, we've already seen that if I were to plot the density of states, it's given by a Dirac delta function at one frequency, delta omega prime minus omega, with of course the number of modes inside the system. You can also multiply this with R if you have more branches. Now, it's easier to understand the density of states first of all in 1D. And why do we need the density of states? If you want to find out the total energy of a system, what we would normally like to do is we would like to integrate over all possible modes, and those modes have frequencies omega. So our frequency is our variable of interest, it's our running variable omega, and this goes from 0 to infinity. And what we would like to do is we want to find out the energy, the total energy of a system. So we find out the energy of a particular mode omega or a particular single phonon omega at a mode frequency omega. We multiply this with the Bose-Einstein occupancy factor or the Bose-Einstein distribution factor, which we've seen is 1 over E h bar omega over kBt minus 1, which tells us how many phonons exist inside the system at that frequency omega. But then we also need to know the distribution of omegas. How is the distribution of omegas looking like? And that is the density of states. In the Einstein model, this was simply a Dirac delta function. So when this Dirac delta function multiplied with all of this integral was sampled at one particular frequency. And we got this very nice result, Cv equals theta e over t 3n e theta e over t e theta e over t minus 1 whole square, and the power for this theta e over t was square. So this was for the Einsteinian case. So now, however, we would like to focus our attention on this g omega. Okay, so the energy of a mode, the probability of occupancy of that mode, or the number of modes excited. In the phonon picture, the number of phonons that are present inside the system. This is the energy of a single phonon. And this is how are these modes or these phonons distributed, which means for a particular omega, how many placeholders exist, how many omegas exist. Not all omegas exist as we know. Some omegas exist, some omegas don't exist. When we looked at the diatomic branch, we found gaps inside the dispersion relationship. So how do we derive this g omega? So first of all, let's look at 1D. In 1D, we know that in the first Brillouin zone, which extends from minus pi by a to plus pi by a, the k values are quantized. right? So we have a discretization of k values, and the spacing between two levels is 2 pi over L. So this is the spacing between two consecutive k levels, 2 pi over L, where L is the length of this chain. So what we're interested in knowing is that if this is the spacing between two levels, how many levels exist in a particular dk? Okay, so dk is some tiny veneer of a section of this one-dimensional solid. This is, by the way, the k-axis. So this is a tiny veneer, a tiny section, an infinitesimally sized section of this k-axis, and we want to find out how many modes exist inside the system. Suppose the number of modes inside this tiny veneer is dn. So this dn would be equal to this thickness dk, and you divide this by the by the spacing between two modes. So if you take this total thickness and you divide this by the spacing between modes, 2 pi over L, which will give you L over 2 pi dk, this is how many modes dn exist inside a particular dk. Okay, so this is a kind of a density of modes inside the k space, but we would like to convert this to some. Now we would like to shift our attention to the frequency variable. So we would like to move from the k to the frequency variable, and we know that the dispersion relationship defines that conversion from k to omega. Nevertheless, this density, this number of modes in a particular region of dk, we would like to equate this to the number of modes g omega that exist in a particular region of d omega. Okay, so this is what we would like to do. But we also notice one more thing. So this is a symmetric function, but omega goes from 0 to infinity technically, or 0 to some upper value. So it's always positive, but k can be positive or negative. So g omega is really picking up k's from here as well as from the symmetrically opposite section which exists at, so if this is k prime, this would be minus k prime. So all of the k's in this region and the k's in this region will give the same omega. Okay, so we would really want to, so this g omega is twice of this, so I would like to put a half here if I would like to make a comparison. So if I look at this relationship that we have in 1D, my g omega d omega is L over pi dk. Okay, in 1D. In other words, my g omega is L over pi dk over d omega, or L over pi d omega over dk. Now in a one-dimensional solid, okay, so this is a general relationship for the density of states in a one-dimensional solid. Okay, so which means that between omega and omega plus d omega, in this interval, the number of states that will exist is, the number of modes that will exist is g omega d omega, where g omega is given by this. That's the meaning of the density of states. So now if I consider a one-dimensional monoatomic chain, I do know that inside the reduced Brillouin zone scheme, the curve looks like a sine curve, right? Where this is 4k over m root, and this curve is sine of qa over 2, or let's use, I'm using k right now, sine ka over 2. So this is our dispersion relationship. This is omega, this is k. Now I need to know this d omega over dk in order to find the dispersion relationship. Now this d omega over dk is simply the slope of this curve, of the dispersion relationship. So the dispersion relationship feeds into the calculation of the density of states. So once you know the dispersion relationship, you can tell what the density of states is. So the density of states here is going to be equal to the slope, inverse of the slope of this graph. So here the slope is some value here. These are acoustic phonons. So at this point, this slope is just equal to the speed of sound inside the solid, which is d omega over dk at k equals 0. If I put, okay, so this is the slope that we have at this point. And that is easily seen. If we take the slope of this curve, this becomes cosine k over 2. At k equals 0, this becomes 1. So the slope is Vs, which is 4 k over m. M is the mass of the atom and root. That's the slope here. That is equal to the speed of sound inside that solid. That's why this is called an acoustic branch. And then the slope keeps on changing, right? Here the slope is different. At this point, the slope becomes 0. At the boundary of the Brillouin zone, at the zone edge, it becomes 0. So now you have 0 inside the denominator. So the dispersion relationship really blows up. There's a discontinuity in the dispersion relationship. So if I would explicitly like to find out d omega over dk, or g omega is L over pi 1 over the slope is 4 k over m, sine, this is cosine ka over 2. Let me see if this factor I've written is correct. Yes, it is. So this becomes some m over 4k L over pi secant ka, right? Ka over 2. This is 1 over cosine of ka. So I can also, so cosine ka over 2 is 1 minus sine square ka over 2, and so on. So this is my dispersion relationship. If I plot this dispersion relationship, this is my density of states. I will get a discontinuity at the zone boundary. At k equals 0, this term is 1. So let's make a plot of g omega. So this is my omega, g omega. So what I need to do really is I would like to write this k in terms of omega. That's what I would like to do. Now I already have a dispersion relationship in front of me. This is my omega. This is my dispersion relationship. So I want to express this k, all of the k's in terms of omega. I have to express, in other words, secant k a over 2 in terms of omega. So let me try to do that. So my sine ka over 2, I know is m over 4k omega. Okay, so I just take that to the other side. My cosine k a over 2 is square root of 1 minus sine square of this. So it's 1 minus m 4k omega square. Okay, so this is m over 4k over m minus omega square. So this is my cosine k a over 2. Therefore, my g omega here is m over 4k L over pi and secant, which is the inverse of this, which will give me 4k over m So I think this kind of goes away and I'm left with this relationship L over pi divided by this thing. So if I plot this, when omega equals 0, I will get some initial value, right? And at omega square equals 4k over m, which is omega is 4k over m under root, this term blows away. This just goes away. Okay, and it's quadratic. In a sense, it's not really quadratic, it's square root of quadratic. So, but it kind of explodes at the edge of the boundary because the group velocity is 0. When the group velocity is 0, you take the inverse of that group velocity, the density of states goes up. So now what this curve is telling us, and there is some initial value which can be easily found by putting omega equals 0 in this relationship. So this value is omega equals 0, this is m over 4k under root L over pi. Okay, so if you look at this dispersion relationship, it really means that in this calculation of the energy, this of course is the energy of a single phonon. This is the Bose-Einstein distribution factor, which tells us how many phonons exist with that mode. But this really tells us that there is a preponderance of states, higher number of states with omegas that are close to the edge of the Brillouin zone than to the center. So this area needs to be emphasized in the calculation of the total energy. So this is a really important concept. So now this concept can be extended to 2D, it can be extended to 3D. Let's see how this folds out in 3 dimensions. So we have derived a dispersion relationship or the density of states for the 1D case, monoatomic that is. Now let's look at a calculation for 3D. So how did we do our calculation? We did our calculation by looking at all the points in the K space and then finding out the number of points in the small section of the K space and then equating it to the density of states and then using the dispersion relationship to find out what the density of states is. So all things are really, really simple. In 3D, the same mechanism can be invoked. So you have now 3 axes, a kx axis, a ky axis and a kz axis. And in the reciprocal space, all of the points, say are, we can break up the reciprocal space into a grid of points in 3D different nets. Okay. So there are many tiny cubes inside this K space. Each cube, so if I focus on a cube, this is what it looks like. And this cube has a volume. In 1D we call that volume delta K. Now the volume is delta V. This is a point, and each of these distances, if this reciprocal space, we are assuming that this corresponds to a cubic crystal system. So the reciprocal space is also cubic. This length is simply 2 pi over L. So the volume in K space is, instead of 2 pi over L, is now 2 pi cube over the volume of the solid, L cube, which is the volume of the solid. So this is the size of one of these infinitesimal volumes inside the K space. So now what we would like to take, we would like to take a thin section inside the K space, totally analogous to the 1D case. That thin section which respects the symmetry of the K space is, instead of being a line, it's a shell. So if I were to draw this shell, let me draw this shell over here. This shell here of some thickness, I'm just drawing this shell in a particular quadrant, here like this. And this extends in 3 dimensions in the K space. So this is Kx, Ky, Kz. This thickness, so the distance of this shell from the origin of the reciprocal, let's call it K. So this thickness is dk. And this total volume of this shell will be 4 pi k square dk. That's the volume of this shell in 3D. Now we do know that each point, each mode occupies this much volume in the reciprocal space. The number of points in the reciprocal space must equal the number of unit cells. Okay? Because the number of degrees of freedom have to be preserved. So we'll just count the number of modes inside this thin veneer, this shell, a very thin shell. Okay? So the total volume of this shell is the number of modes dn, once again in 3D. We just take the volume of the shell, which is analogous to the dk over there. Now we have 4 pi k square dk. And we divide this by the volume of each infinitesimal cube, which corresponds to the size that one mode takes inside the reciprocal space, which is delta Vk. This will give us 4 pi k square dk. Delta Vk we've already found is 2 pi cube over the volume of the cell. Now this must equal g omega d omega. G omega d omega, now we do not multiply it with 1/2 or anything else, because this dk is a magnitude. This is the entire sphere, the entire annular ring in 3 dimensions, not in a single quadrant or a single octant, in the entire, all of the 8 quadrants inside the reciprocal space. So we do not multiply this with any factor of 1/2 or anything else. So this is our g omega, and the next thing that we need to do is we would like to express this k in terms of omega, and that will come from the dispersion relationship. So let's try to do that now. So my g omega is, so if I simplify this, this is 4 pi k square, this is 8 So 4 over 8 is 1/2 2 pi square k square dk v dk d omega. This is v k square 2 pi square 1 over d omega over dk. Okay, so this is the density of states in 3 dimensions. I need to know the dispersion relationship in order to find the group velocity. And as we've seen that for 3-dimensional solids, the dispersion relationship is also dependent upon the direction in the k space that you're taking. So if you have the dispersion relationship, you find the group velocity, you put it in the denominator, and you compute this value, you'll get g omega. Wherever there is this group velocity goes to 0, which happens at zone boundaries, it can happen at other points as well. This dispersion relationship, this kind of dispersion relationship will give you an singularity in the density of states. Okay, so I'll give a homework problem in which you would ask you to calculate this for a diatomic 1D lattice. So equipped with this description, now let's try to variation or the next improvement or refinement to the Einstein model, which is called the Debye model. Now what the Debye model states is that the dispersion relationship, so this is a model. What this states is that for any 3-dimensional solid, if I have k and omega and I would like to find out the dispersion relationship, then it's a straight line. And this is what happens for sound. So the Debye model states that omega equals Vk, where V is the speed of the sound inside that solid. So this is just the Debye model, okay? And this will really work inside true solids for the acoustic branches, because at the acoustic branch, at the k equals 0 point, this slope does represent the speed of sound. But the Debye model goes one step further and it assumes that this dispersion relationship, instead of being curved or something else, it's a straight line at this slope. So this is our presumed dispersion relationship for the Debye model. And it's a good model when k is small, which is long wavelengths. So now we would like to use this dispersion relationship and find out the density of states corresponding to this dispersion relationship. This d omega over dk is simply a constant, which is the speed of sound. This kind of derivative is called the group velocity. And this group velocity in this case is equal to omega over k, because this is a straight line. So this is the phase velocity and this is the group velocity. So there is no dispersion here. This dispersion ratio means that really it's a straight line. It means that this is dispersionless. The omega does not depend upon, it only depends linearly upon k, the speed is a constant. So if we insert this d omega over dk in here, in the Debye model, so now I'm using the Debye model density of states to try to describe my solid. This is the volume of the solid, k square 2 pi square. This will become v, so 1 over v square. Now k square is really omega square over v square. This is v, sorry. This is v. So this becomes v, this becomes omega square 2 pi square. There's already a v, another v square comes in, so this becomes v cube. So this is the density of states in the Debye model, which is now a parabolic function of omega. So the density of states in this Debye model is omega, and you have the density of states here for the Debye model, and this is just a parabola. Okay, proportional to omega square. Now we also do know, in our previous lecture we've also seen that this dispersion relationship cannot go on forever, because at the outset it seems that these omegas can go from 0 to infinity. But if you take the integral of g omega for all omegas, you should just get the number of modes. And by the way, we are only talking about, it's a three-dimensional solid, so we're just talking about one polarization or so. So there is only one polarization that we're focusing on, because the wave can be longitudinal, it can be transverse. We would have to multiply this with the number of polarizations that can exist. But so far, we are oblivious to the polarization, just for one single polarization. So if this is really going from 0 to infinity, the integral cannot be countable. So what Debye did is that he put a limit on the upper frequency omega d. So this curve really goes up till some omega d, some Debye frequency, such that the area under this part remains equal to n. Okay, and this omega d can also be calculated. So you can just take this g omega and insert it in here, equate this to n, you will get omega d. So what you could do is, this is my d omega. My g omega is v over 2 pi square small v cube speed of sound, and g omega omega square 0 to omega d. This gives me v omega d cube over 6 pi square v cube. This must equal to n, which really means that my omega d cube must equal 6 pi square n over v. V is the total volume of the solid, to v cube. So this small v is the speed of sound. In other words, my omega d must be 6 pi square. I'll call this the density of atoms, the number of atoms per unit volume, 1 over cube. This is my Debye frequency. So this integral is limited on the upper side by this Debye frequency. Now let's calculate the total energy inside this Debye model. And in order to calculate the total energy, that's really something very simple. It's just given by that formula over here. So now this is for the first time that we are looking at a density of states being contributing to the total energy of this gas of phonons. So the energy inside the system, of course corresponding to a single polarization, is given by d omega, where omega ranges from 0 to omega d. The energy of a phonon, h bar omega, we're ignoring the 0 point energy, because when you take the derivative with respect to temperature, it just goes away. So this is h bar omega, and then we have E h bar omega over kBt minus 1, and we have this g omega over there, which is v 2 pi square v cube, this is capital V, and then omega square here. So this will become omega cube. So this is my total energy inside the system. So what I would like to do, I would like to put this term, let's call this term x, kBT x. So d omega would therefore become kBT over h bar dx. d omega kBT over h bar. So I'm left with v over 2 pi square v cube. This goes from 0 to some x d. d omega is dx kBT over h bar. So h bar omega cube. Omega cube is kBT over h bar cube x cube. Right, so this is my total energy. This is V 2 pi square V cube kB T over h bar raised to power 4. An additional 1 over h bar, oh sorry, additional in the numerator, h bar 0 to x d dx x cube okay. So this is my energy inside the system due to all the frequencies, due to all the modes in a one branch, one polarization only. This is a really nice result. And you can plot this. You can find out what this integral is and plot it. So what we would like to do is we would like to look at two scenarios. High temperature. This is the energy. So my x is h bar omega kB over T. When temperature is large, x is small. So when x is small, this becomes 1 over x. So 1 plus x minus 1 is x. X cube over x is x square. So this integral alone can be approximated as x cube over x, which is x square, which is x cube over 3. Okay, so all right, x cube over 3. So the energy at the high temperature regime is V over 2 pi square V cube kB T over h bar plus 4 h bar x cube over 3. So 1 over 3. This is xd cube, right? Because of this upper limit. So xd is h bar kBT omega d, which we have already found. Okay, so I just use this expression, replace omega with omega d, I'll get xd. So I just need to kind of simplify this a little bit and the result will be really nice. So let's go through this ordeal of simplifying all of this. This is V 2 pi square V cube kB T cube or kBT h bar cube. So this is h bar 4 h cube. This is another h bar. But I've already taken this into account because I've reduced this from 4 to 3. And 1 over 3, I get a 6 here. This is omega d cube, right? So omega d cube is 6 pi square n over v speed cube. Okay, really nice. So the 6 pi square goes away, this v cube goes away, v goes away, and I am left with kb capital T h bar n. Okay, ये ठीक है. I have xd cube. My xd is given by h bar omega d kbt. So I need to take the cube of this, so I get h bar cube kbt cube, correct? Omega d cube. All right, so from this point onwards, let's see v 2 pi square v cube. Now this comes out as kbt over h bar. This is raised power 4, this is raised power cube, this is the reciprocal, so just power 1 h bar over 3, and then I have omega d cube, which is 6 pi square n over v cube. Okay, so this 2 pi square, this pi square goes away, this 2 into 3, 6 goes away, this v goes away, this h bar goes away, and what am I left with? This v cube goes away. What am I left with? I'm left with n kbt. Beautiful. At high temperatures, the thermal energy, which is a classical result for n atoms, is n times kbt. This is number of modes. This is the energy of each mode. So you reproduce the thermal the classical result. And if I would just like to find out the heat capacity at this high temperature, the heat capacity at this high temperature is simply the derivative of this with respect to temperature, which is n kb. And if we have a three-dimensional solid, you have the possibility of a mode with a transverse polarization, two kinds of transverse polarizations, x and y, and a longitudinal polarization. So you have three modes really with each of the n atoms. So for a three-dimensional solid, this will be 3n kb for a monoatomic system, which is exactly the same result that we have for the Einstein relationship. And at the high temperature limit, the Debye result and the Einstein result, they match. And they match with all the possible classical predictions. They also conform to the Dulong-Petit law. At low temperatures, very low temperatures, extremely low temperatures, you can correspondingly find out the energies. So in the low temperature case, this x, which is h bar omega kbt, low temperature, this becomes really, really large. So when this becomes large, what you could do is this upper limit xd for large temperature becomes, you can replace this xd for small temperatures, this becomes really, really large. So this integral upper limit could be replaced by infinity. So in the low temperature regime, this integral can be written as 0 from 0 to infinity dx x cube divided by e raised to x minus 1. And you can solve this integral in a simulator or by hand, and you get some value. That value will be something pi raised to 4 over 15. You put that value into your energy, you differentiate with respect to T, you'll find out that your heat capacity is proportional to T cube. Okay, so this is something I would leave as a homework for you to do. All in all, what we've seen is that in the Einstein model, you have a density of states given by a Dirac delta function. Only one mode exists, and you get a curve for your heat capacity, starts off at 0 and plateaus off to 3n kb. For the Debye model, this is the Einstein model. For the Debye model, what you've done is you have derived the density of states Debye, which starts off at a non-zero value and goes parabolic and is cut off at a particular omega d. So this is a cutoff frequency called the Debye frequency. No modes exist beyond this omega d. That's the Debye model itself. You get a curve which is again extremely similar to the Einstein curve with slight variations, and that curve is given by the temperature derivative of this energy relationship. In the high temperature regime, both of these values match. In the extremely low temperature regime, if I zoom in on to this, in the low temperature regime, this is my T, this is my CV, I will get an approximately cubic relationship with respect to T. Okay. So, but this temperature can be extremely, extremely small, almost at the order of 1 Kelvin. So once again in the Debye model, what is really, really interesting is that you can impose an upper cutoff frequency, a Debye frequency, and a curve. This curve itself, if you take the derivative of this, this will only depend upon this parameter theta d, which is h bar omega d over kb. It will be defined by a single parameter. So this is how you use the concept of the density of states to find out the heat capacities of solids. I'm going to post a homework number 4, which is due before the midterm. And the second thing I would like to mention is that there will be 2 more lectures on this topic. One lecture will do an explicit derivation of the equivalence of the classical model from which we wrote down the equations of motion in the harmonic approximation. We find out the energies, we have a classical description of the energy. We would like to quantize that model and do an explicit derivation of the idea of phonons. So this is called the framework of second quantization. And in the last lecture that deals with crystal oscillations, I would like to look at inharmonic effects, because there are certain effects that cannot be described by this harmonic approximation. One of them is thermal expansion. The other is thermal conductivity. So in this model so far, the phonons have infinite lifetimes. Once they are created, unless there is an external probe or an external stimulus, they will remain there. They have infinitely long lifetimes. So they will not scatter. If they move inside a solid, these particles move, contribute to thermal conductivity, they will not scatter. So every material should have infinite conductivity. But the point is that these phonons also scatter, they have finite lifetimes. And that cannot be described within the harmonic approximation. So the last lecture will be talking about these subtle harmonic effects. Thank you very much.